You've conducted a literature review, and now you have a research question. Let's take a look at the data.
Raw data consists of long lists of numbers and labels that don't seem to be very informative. Raw data lacks context. Exploratory data analysis is what you use to make sense of the data. You do this by converting data from its raw form to a form that makes sense, that has context, that tells the story you want to tell. Basically, exploratory data analysis consists of organizing and summarizing raw data, looking for important features and patterns in the data, looking for any striking deviations from those patterns, and interpreting your findings in the context of the problem or research question. We begin exploratory data analysis by looking at one variable at a time, also called univariate analysis. In order to convert raw data into useful information, we need to summarize and then examine the distribution of any variables of interest. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values.
If we were studying a small number of observations, we could do this with a pencil and paper, a calculator, or even in our heads. The data sets you're working with often have thousands of observations. Working with such large samples is only achievable if we use statistical software. These software programs require the use of syntax or formal code to retrieve, analyze, and manipulate data. Learning to write code, learning the proper use of syntax, can really expand your capacity for engaging in statistical applications and is a central skill you'll learn in this course. This skill will also greatly expand your capacity for engaging in deeper levels of quantitative reasoning about data.
For this course, you'll be using Stata. Stata is a very powerful statistical software package. Looking at all the windows, menus, and features, though, can be rather daunting. So it's important for you to realize that this course will introduce you to the basics of Stata. You'll learn what you need to know to get started asking and answering interesting questions about data.
In the beginning, it may feel like you're learning another language. Basically, you are. As you work through your project, you should begin to feel more comfortable implementing the various decisions you'll be making about the data. When you need help, seek it from your course moderator, professor, your peers, or from course discussions.
To open the Stata software, simply navigate to the location the software is stored on your computer. Alternatively, you can go to your computer's search bar and type in Stata. Once you've launched Stata, you're ready to get started. This is your main screen, which will be the first screen to appear whenever you open Stata. We'll get back to this main screen in just a minute to explore it a bit more. But for right now, let's start by opening a do file, which is a separate screen we can use to write our code. To do this, click on the icon in the list of icons at the top of the screen that looks like a pencil writing on a piece of paper. This will open a new window that looks much like a word processor. The do file is where we'll write and eventually store all the code we use for data analysis. However, before we jump into working with our data, there are a few small preliminary steps we should do first. It's good practice to always begin your do file by setting the working directory that you plan to use. A working directory is essentially just the location on your computer that you want to be uploading data from or saving data to, such as a specific folder on your desktop. By setting a working directory, you're telling Stata to use that specific location as its home base. To do this, you'll use the cd command, which stands for change directory. Then, in quotation marks, write out the file path that navigates to the specific directory you wish to use. Once you've done this, you'll want to write a second line of code to open a data set that you'll be working with. You will use the use command to do this. After use, simply type in the file name as it appears in the working directory you just set. Because of the cd command, Stata already knows to look in that directory. So you only need to tell Stata here the name of the file you want to open. Finally, you'll include a comma and then a clear at the end of this command line. Comma separates required and optional arguments from options for the command. That is, the pieces of the syntax that are absolutely required for the code to run, and the pieces of syntax that are not strictly necessary. Here, the command itself, use, and the file name are both necessary, so they're part of the required argument. Clear, on the other hand, which tells Stata to clear out any data that might be already stored, is not strictly necessary, and so it's an optional argument that comes after a comma. Since we just opened Stata, we know there's no data already in memory, but it's a good practice to include the clear option anyway. It's also possible to open a data set by using the point-and-click features of Stata by going back to the main screen, clicking File, then Open, and then selecting the data set from your computer. Most commands in Stata can be performed using point-and-click as well. However, since this class emphasizes writing code, you'll learn how to do all of this through coding. Notice that Stata uses color coding to help you write and debug your program. Blue font indicates a Stata command. Commands are a primary part of Stata's programming language. They're part of the established Stata lexicon. Most Stata statements begin with a command. Burgundy font indicates that Stata considers this section of your statement part of a string. A string in Stata consists of consecutive alphanumeric or other characters enclosed by double quotation marks. Your file path in the cd command line is an example of a string. Green font indicates these are your comments, the code writer's own statements. They're kind of like notes to yourself about part of your program. Whenever you use an asterisk or two slashes, Stata will turn the rest of that line green and will read the rest of that line as a comment, not a command to be executed. Comments can either be added at the end of a line after a command or on their own line. You can also use 3 slashes to make a long and wieldy command occupy multiple lines, and thereby making it easier to work with. These slashes will also appear in green, just as your notes and comments appear in green whenever you use an asterisk or 2 slashes. Black font is used for all remaining parts of your code, including any variable names you might include in a command or any optional arguments. Stata is case sensitive, so be sure to use the correct capitalization to write your programs. All commands are lowercase. Nisark_PDS is the actual name of the Nisark data file. If you chose the Mars crater dataset, Nisark_PDS will be replaced with Mars crater_PDS. For the National Longitudinal Study of Adolescent to Adult Health, the name would change to add health_PDS. If you chose the Gapminder dataset, the name will simply become Gapminder, and so on. Sometimes datasets might be too large to load into Stata, depending on your license. If this occurs, we can tweak the use command just a bit to deal with this. Right now, the command we're working with is use dataset name, clear. If the dataset has too many variables, we can tell Stata what specific variables to keep by changing this to use, then a list of your variables from the dataset separated by spaces, using, dataset name, clear. Even if your full dataset can be loaded to Stata, you may want to consider subsetting this way to make the dataset more concise for your purposes. Remember to refer back to your codebook to find variable names and spellings. You may have to look directly at the data set to see if your variables are capitalized or not. In this example, you can see what we mean by a long and wieldy command. We've subset the Nisark dataset to make it more concise, yet the variables we'll be using still makes a very long list. We can use the 3 slashes to make this very long command an easier to read multi-line command. It's good practice to tab in the second line of a multi-line command. Any subsequent lines will automatically tab in after you tab in the second line. This is an easy visual way to know where your command begins and ends. And remember that your template for the use command in this situation is use, list of variables, using, dataset name, comma, clear. So far, we've written 2 lines of code, but we haven't yet told Stata to actually perform these commands. To do this, we'll highlight both lines of code and then click the Do or Execute button on the top right of the Do file. Comma separates required and optional arguments from options for the command. Note that you need to highlight the line of code to execute it. This will execute the commands and display the results in the main window of Stata. Now that we've set our working directory and opened our data set, a good habit to get into is to sort the data according to the variable that uniquely identifies each observation, that is, the unique identifier. In the NISARC dataset, the unique identifier is called ID num, so this line of code, sort ID num, is telling Stata to sort the data in the NISARC dataset we just uploaded by the variable ID num that exists within that dataset. Since every letter in the variable ID num is capitalized, we must capitalize the whole name in the command line of our do file. Remember to highlight and execute the command after you've written it. By consulting the codebooks, you'll find the unique identifier for the Mars crater data is ID. The unique identifier for the Add Health dataset is AID. The unique identifier for Gapminder is country, and so on. Now that you've sorted your data, all procedures that follow will request specific output or results. Now's the time to save the program you've started. First, we need to save the do file that we've been working with so far. To do this, click on File in the Do File Editor window, then click Save As. Feel free to erase the default name and rename the program as you like. It's important to note, however, that this saves only the do file and not the data. If we only save this file, we've only saved the text of commands that we've written. If we make any changes to the dataset, those changes will not be saved by saving the do file. There are 2 ways to deal with this. The first is to save an updated dataset by going back to the main screen and clicking on the Save icon, which will save the dataset. This can also be done by using the Save command in the Do File Editor. The template for this command is Save, File Path, comma, Replace. The second way is to make sure that all your code in the do file is as comprehensive as possible when saving. This way, when you open your do file next time, you can execute all the lines of code and all changes you made to your data will be made again. For this course, we'll be using the second method. However, please feel free to use whichever method makes the most sense to you.
Remember, we stated exploratory data analysis begins by looking at one variable at a time. This is called univariate or descriptive analysis. In order to convert raw data into useful information, we need to summarize and examine the distribution of any variables of interest. The variables of interest are the variables of interest to you, the researcher, in answering your research questions, addressing your research problem, and telling the story you wish to tell with your research. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values. Here's an example.
A random sample of 1,200 U.S. college students were asked the following questions as part of a larger survey. What's your perception of your own body? Do you feel that you're overweight, just about right, or underweight? This table shows part of the data, 5 of the 1,200 observations. Information that would be interesting to get from this data includes what percentage of the sample students fall into each category, or How are students divided across the 3 body type image categories? Are they equally divided? If not, do the percentages follow some kind of pattern? There's no way that we can answer these questions by looking at the raw data, which are in the form of a long list of 1,200 responses. That's just not very useful. However, all these questions will be easily answered once we summarize and look at the frequency distribution of the variable body image. That is, once we summarize how often each of the categories occurs. In order to summarize the distribution of a categorical variable, we first create a table of the different values or categories the variable takes. How many times each variable occurs, which is the count, and more importantly, how often each variable occurs, which is expressed by converting the counts to percentages. Now that we've summarized the distribution of the body image variable, let's go back and interpret the results in the context of the questions that we posed. What percentage of the sample students fall into each category? How are students divided across the 3 body image categories, and are they equally divided? You can see that most of the sample, that is 71.3%, felt that their weight was about right, and that a comparatively small percentage felt underweight at 9.2%. The overweight category was 19.6%. This can be done in Stata using the tab 1 command, which is what you use to generate distributions for the variables of interest that pertain to your research question. The tab 1 command is typed as tab 1 and is followed by a list of variables that you would like to examine.
For my research question, I'm interested in looking at the association between how much a person smokes, that is, quantity and frequency of smoking, and the presence or absence of nicotine dependence. Going back to the NESARC codebook, you may recall that I have a number of variables that measure smoking behavior and nicotine dependence. It's the actual name of the variable, rather than the longer descriptive name, that I'll include in my program in order to generate frequency distributions. I have the names of each of the variables circled here in red.
Here's an example of a NESARC program using the tab 1 command to look at the distribution of variables that reflect smoking frequency and quantity and nicotine dependence. When you add the tab 1 command with your own variables of interest from the data set you've chosen to ask your research questions about, and then click Execute, you've written an entire Stata program. You will build on this program as you progress through your project. Before you run the program, it's always a good idea to save it. Click the Save button at the top of the Do File Editor window. After you save the program, you can run the specific command you're interested in by highlighting that line of code with your cursor, then clicking on the Execute button, which again is the rightmost icon at the top. This will take the command or commands that you've highlighted and execute them in the main Stata screen. Now that we've clicked Execute, let's return to the Stata main screen and take a look. You can minimize your Do file so that the main screen is visible. There are 5 different windows within Stata's main window. On the upper right-hand side, you'll see the Variables window, which lists all the variables that are available to you after loading a data set into Stata. When you first open Stata, no variables will be listed because no data set has been loaded yet. However, after executing the Use command, all variables for the data set you listed will be uploaded into Stata and will be visible in this window. The bottom right window is the Properties window, which tells us basic information about our data set, such as how many observations it has and how many variables in the data set are being used. In the bottom center, you'll see a small Command window. Commands can be executed 2 ways in Stata. The first is by opening a do file, writing a code in the do file, and then executing that code just as we've done. The second way is to write that exact same code in the command window and hitting Enter to execute it. Both ways are possible. However, the do file is easy to save, whereas the command window just executes commands and does not save them easily. This is the reason we'll emphasize using the do file editor and not the command window in this course. Whenever you execute a command, either in a do file or in the command window, it will appear in the review window at the far left of the screen. This is your command history. Any commands in this window listed in red have errors, so this is an easy way to check to see if Stata has identified any errors in the code you've just tried to execute. Finally, the large window in the center of the screen, the results window, shows you the results and error messages. If you do find any red errors listed in the results window, go back to your code, correct the errors, save the corrected code, and then run your command again. It's important to note that Stata will stop running commands whenever it encounters an error. This is to say, if you try to run several commands from your do file at once, Stata goes through those commands one at a time in order, and if it sees an error, will report that error and stop running. It will not try to execute the remaining lines of code. If no errors are listed in the results window, you'll see the results of your command. In this case, it will be the distribution tables you generated. In addition to these 5 windows, you can click on the icon at the top of your screen that looks like a spreadsheet with a magnifying glass over it. This is the Data Editor button. This will allow you to see all the variables and observations in the data set. At the bottom of this window, you can see the number of observations. There were 43,093 observations read from the dataset NESARC_PDS. That's good news since we know that's the number of observations or individuals in this dataset. If the number of observations seems incorrect, it's possible there may be a problem with the program that processed the data incorrectly rather than actually generating an error message. In that case, you should probably go over your commands very carefully to see if your data has been processed correctly. If your program ran successfully and there are no error messages in the results window, then go ahead and look at your results to see the frequency tables that were generated for each of your variables. Because the actual variable names are cryptic, it's a good idea to give them labels that are more easily interpreted at a glance. We'll use our sample NESARC program again as an example and show you how to generate variable labels in your program. The command to label your variable is quite intuitively called label variable. After this command, list the name of the variable you want to label. Then after that, in quotation marks, what label you want to assign it. You can reproduce this line as many times as you need to make all the labels you'll need for your variables. Then save your program and execute these new commands by highlighting them, then clicking the Execute button. This has changed the labels of each of these variables. Once these commands are executed, we can go back to the tab 1 line and execute that command again. This will generate the frequency tables again, but this time with the updated variable labels. Check the results window, which shows no errors, and then view the results. Now the frequency distribution includes each variable's label, which appears in the top left-hand corner of the table in the output. Look at the first table, which shows the distribution of responses for the variable tobacco dependence in the past 12 months. The NESARC codebook shows that 1 means yes and 0 means no. This first column of response options, 0 for no and 1 for yes, is followed by a column that shows the frequency of each response. The table also shows the percent of individuals with and without nicotine dependence, the cumulative frequency, and the cumulative percent. By consulting the codebook, you can interpret and describe each of these frequency tables in the same way. Once you've examined frequency tables for your variables, the next decision you need to make is whether you want to subset the data and ask a question based on specific observations, or whether you want to ask the question of the entire sample. In other words, are there particular rows in the data set, that is, individual observations that you want to keep and others that you want to exclude. For example, what if we are most interested in the association between smoking and nicotine dependence in young adults who may still be establishing their smoking patterns? We might therefore want to examine only those adults who are 25 or younger and exclude all adults older than the age of 25. We might also decide we want to focus on recent smokers rather than individuals who have smoked more than a year ago. So the original research question for our example is further clarified to include the association between smoking and nicotine dependence, but only among young adults who have smoked in the past 12 months. The research question is not changed. Rather, the question will be asked based only on a subset of the observations that are available in a specific data set that will help answer the research question. To implement these decisions, we'll go back to our do file and add an additional command to our program, the keep command. The way we'll be using this command will require what is called a logic statement. Logic statements require one or more operations. Here's a table of common operations used in Stata. These include equal to, not equal to, greater than, less than, greater than or equal to, and less than or equal to. Note that the is equal to operation is two equal signs and not one. This is a common error in Stata coding, so it's good to keep this in mind. The following logic statements will need to be added to this program in order to keep the specified subset of the observations now to be used as the basis of the research question. Keep if check 321 equals 1, which is the variable for cigarette smoking status in the past 12 months, and keep if age less than or equal to 25, indicating selection of only those individuals less than or equal to 25 years old. We can either run these as separate commands in two lines or connect these two logic conditions into one statement with an ampersand. Once this code is written, save your do file, highlight the command, and execute it by clicking the top right icon. On your main Stata screen, you should now see the number of observations in your data set decrease to 1,706. Now that we've done this subsetting, let's also add the age variable to the tab 1 command so that its distribution can be examined. When this do file is saved and the tab 1 command is executed again, you can see frequency distributions for each of the variables, but only for the 1,706 individuals aged 25 and younger who reported smoking in the past 12 months.
I can be confident that I am now working with this sample because, as you can see, all of the 1,706 observation has a 1, meaning yes for having smoked in the past 12 months. And if I scroll down to the distribution of age, I can see that only 18 to 25-year-olds are included in the sample. If for your own research question you are completely unsure at this point whether or not you want to limit your question to a subset of observations, no worries. In that case, there would be no need for you to add any additional logic statements to your program. This is always a decision and an example that you can revisit in the future.
As we mentioned before, with the green text in a do file, there's a way to add notes to your program to help you remember what specific lines of code do. As you keep adding to your code, it might become difficult to remember why you wrote what you wrote. You can comment out your notes so that Stata does not read the notes as actual program statements. Whenever you use an asterisk or two slashes, Stata will turn everything green for the rest of that line and treat the rest of that line as a comment. Here's a note added to our example code. This is a reminder that we're subsetting the data to include only past 12-month smokers age 18 to 25. The note is written in green within the program, so you can be confident it will not be read as Stata syntax. You should definitely use this commenting out technique early and often as you build your program. These notes can be very important because they will help you keep track of decisions you've made and actions you've taken in writing your code. You now have the tools you need to complete assignment 2. For this assignment, you should write a Stata program that displays frequency tables for the variables that you've selected for your research question.